ultimo. Ok.
Okay, thank you very much for the invite. Thank you to Tatiana. I wasn't sure what to present, and then in the meantime we got this astonishing result. So I decided to focus the talk on this paper that you might or might not have seen on the archive, which deals with the James Webb Space Telescope unique detection of actually strong feature that pertain to a particular evolutionary phase that has been debated over the past 25 years, so only a bunch, but I'll get to that. The paper is led by Xin Lu, who is a PhD student at the University of Nanjing. Under the supervision of Emanuele Daddi, I've been asked to join after they found the result, and we will make clear why. I need to acknowledge Alvio Renzini, but also Laura Greggio for the model revise that we did in 2013 that will play a particular role in what I'm going to say. To provide a bit of introduction for those who need, as requested, the study of modeling the spectra of galaxies is embedded in galaxy formation evolution on a cosmological timescale. There are a lot of complicated processes that are mostly modeled through factors and empirical calibration, like the conversion of gas into stars, feedback that may occur through stars, that will occur through stars, and may through massive black holes, how mass grow through dark matter merging. And when we got our PhD, we have been told that dark matter would have been found in a matter of a couple of years. This is what Joe Silk found, and now 26 years later, we are here, and we still don't know, but it's a major thing in modeling the formation of galaxy and the growth from the Big Bang. And also very topical is how to stop star formation, which also seems not to be completely simple. So in general, when you have a deep field of galaxies, in order to make galaxy formation evolution, you need a lot of physical properties that include distance or redshift in that, age and formation epoch, star formation history, chemistry in its detail, the mass in stars, the mass in remnants, and the dark matter. And it was long understood that this can only come from the detailed modeling, theoretical modeling of the galaxy spectrum, because all this, the continuum, but also the spectral line of key elements actually trace the formation of galaxies. So you might have seen this slide already, but it's useful to remind that who actually laid out the foundations of what is called evolutionary population synthesis is Beatrice Tinsley in this series of papers, and Alvio Renzini contributed shortly after she passed away by detailing something that I use in my model that is called the fuel consumption. But essentially, differently from the optimized population synthesis, which adjusts the galaxy spectra to an arbitrary combination of stellar spectra, which may not be physical, the evolutionary synthesis make explicit use of stellar evolution if available, and that will be an important point on dealing with certain phases. And the contribution of stars at different phases is weighted by energy and time scales. There has been two approaches, main approaches, the isochron synthesis, which was pioneered by Gustavo Brusual and taken by Brusual and Chalot, and in fairness, all other researchers in the field is quite immediate because you get an isochron, and the isochron have been more and more complete over the years. At the time of Beatrice Tinsley, the latest point on the isochron was actually shortly after the main sequence turn off. The alternative approach is called the fuel consumption theorem, laid in a preceding paper by Renzini and Buzzoni, 86, which Buzzoni took in order to model all the population, and I took in order to extend this to young and intermediate age population. So the problem of the integrated light of a galaxy is that you know that you have all the stellar phases and also all the stellar generation that might have been in the galaxy, all summed up together. So the models I'm talking, their realm is not the resolved stellar population in the local universe, for which people use a CMD result diagram, although what I'm going to say will also impact on that type of study. Here, you have this blob of light and you need to make sense out of it. And this was called the problem of the pig by Renzini and Buzzoni, 1986, which actually made clear that you need to take into account every phase. There are some that are very short, some that contribute very little, some that may contribute nothing in galaxies, but a lot in globular clusters. But these are the main thermally active phases of stellar evolution. So a careful galaxy model will require account of all these phases for the energetic and the type of spectra. It may still fit the data well, but it will fit the data well for parameters that are not physical. So the last, indeed, major stellar evolutionary phases to be dealt with in evolutionary population synthesis, particularly in my PhD thesis, is the thermally pulsating asymptotic giant branch, which is the major part of the asymptotic giant branch, so the double hydrogen and helium shell burning towards the end of the lifetime of the star. The TP, or thermally pulsating asymptotic giant branch, is the energetically relevant. There is an early part that is called early asymptotic giant branch that I showed there in 98. It only contributes to 4% of the total energetic. The others instead may contribute substantially, and we will see what substantially means, to the light. And also notice, this is the HR diagram, but in an observed plane. It is a strongly luminous phase. It is the most luminous in the HR diagram. And it is, this is color, but the temperatures along the phase are cold, let's say very, there is a trend. Therefore, this phase will contribute the high luminosity mostly to the near infrared part. The phase in itself, it is unclear how it lasts, how long it lasts, because there is strong mass loss, actually removing layer of the stars, and because this is an envelope burning stage, this will actually speed up the evolution. And so in principle, the overall phase could just last 3 million years or thereabout. Besides the short phase with the high luminosity, the type of stars, and this is amazing that I will show you the James Webb just see, are actually very peculiar. We're speaking about oxygen-rich stars, which have strong oxygen molecules of the type of CO, and not only, and especially carbon-rich spectra, which comes mostly after the convective dredge-up further during the phase. So if you are going to see this feature especially, that has no confusion with other stellar phases, while the oxygen-rich, as I would say, can also occur at the tip of the red giant branch. It was recognized, and this is the only bit on which we all agree, that is very tricky to model fully theoretically, as every phase when it is affected by strong unknown mass loss. So, essentially, if the evolutionary population synthesis need at least these three ingredients to properly include the stellar phases in the total spectrum, namely energy, the timescale, and the type of stellar spectra, both of the three of them, these are linked, are actually unconstrained for thermally passing asymptotic giant branch star. Energy and timescale because of the strong mass loss, and also the spectral emission that you need to feature for this type of phase is happening in cold regime. There is molecule formation, and all of this is very hard to model with model atmosphere, although there are attempts, but they comprise a sparse spectrum. So to give you a sense on how this spectra look like, so that then you will see the galaxy spectrum, a carbon-rich empirical observed from these guys in the whole rest frame from the optical to the near infrared is look like this, with a lot of hard edges due to the carbon nitrogen, that's called cyanide molecules in carbon rich. The temperature will mean that the coldest types actually peak really in the near infrared, the spectral energy distribution. The oxygen rich is a different type of absorption. You see, they are actually very deep, but a bit more rounded. And that's affected by mostly vanadium, titanium oxide, and zirconium that we will see. Zirconium is also present here. So these are the type of spectra you should include. If you go through the Kurux library that population synthesis uses, you won't find this type of spectra. So early population synthesis model fully based on the Kurux library would pick some M giants as a trade of these. That, of course, won't give you the feature that you would like to model if they exist. So as said, these things has been hotly debated in the literature, but I would like to really go through what happened over the past 20 years. It is very actually in the newest model. So the problem is how much ATP we need to include and at what age it becomes relevant in a galaxy evolving galaxy in a stellar population. So the consensus among people working in the field is that the AGB cannot be modeled fully theoretically, although it is a consensus that came after my PhD thesis, because before, the early asymptotic-giant-branch was actually traded for the whole phase. So the theoretical energetic must be calibrated with data, even in terms of calibrating the stellar tracks, like the work of Paolo Marigo and Girardi. So there are two approaches that we will see here. And there the dissensus come that amazingly the James Webb Space Telescope data were able to actually clear what to calibrate and how to do it. What I did back here, following schools like Ferraro and collaborating with Delphi Global Cluster, we're doing this and integrated on resolve counts that I will show later, is to use individual globular clusters, because for them, the age is well defined. And it is still well defined if they have multiple population, which amounts to a reasonable amount anyway in mass. So, as difficult as the job is, if you take the Magellanic Clouds clusters that notoriously, well before my work, were designing actually the TP-AGB. So it was always a wonder why we should see it in the Magellanic Clouds and not in external galaxies. For this, you take the ages. Marigo and Girardi and Brusoil and Charlot decided for another type of calibration, which is the population of filled AGB carbon and oxygen stars in the Magellanic Clouds or in the Milky Way, which means you actually model the light of a galaxy for which you need to know the star formation history, which is super uncertain. So among the two, let's say, I always follow that because it was clear, also to correct it, as I will show. And Koroy and Gang follow this approach. So we have these two things, and they result in different models. So when you do this job, you do the energetics, it was immediately clear that there were differences. Here you see, apologies for missing the Y label in both, the fractional contribution by the major evolutionary phases after the inclusion of the asymptotic-giant-branch to an evolving stellar population with ages from 30 million years to 15 billion years. Just highlighting the actor of this talk, in my models, the AGB become nearly 40% of the bolometric at an age that starts around 0.2 gigayear and peaks around 9 billion years. Earlier, Brusoil and Charlot did this type of plot, and I actually took inspiration for this plot to do my own. And then you see the AGB is these things. First of all, is never the dominant contribution to the bolometric. This you can already see. Ignore the bands because that's not the point. Which highlighted that the two energetic were different. Then you get all your models. This is just to remind what we're talking about. You use that energetic to calculate spectra. And what happened was that in 2005, so 20 years ago, I published this model that opened a huge controversy, sorry. But the cool thing was that at the given age, the model including the thermally passing asymptotic-giant-branch, and what I show here is the theoretical spectral energy distribution of a single burst of about 1 billion years, would show a higher level of near-infrared flux, but especially carbon, oxygen, water, C2, CN, titanium oxide, and others, and the CN especially, in virtue of including those spectral types. When I drop the phase, I get a smooth near-infrared featureless ACD. And then people seem to find actually that you needed this enhanced near-infrared and also feature to explain high-redshift galaxy data. This is the first paper who did it exactly at the same time of my paper, because they were not able to fit the Spitzer data of this redshift 1 galaxy with spectroscopic redshift using the Bruzo-Allen-Charlot 2003, which is the red line. They should have used red for my models because they have more red flux, but instead it's the opposite. So my model are the blue, and they seem to show an amazing, actually amazing agreement in this case. These are HST data. If people would have only fit up to 6,000 angstrom, both models would have worked well, and you would have been trapped in a degeneracy between the ages that would come out of this, which reinforced the notion that, in fact, it's better, much better to have a wider wavelength range, with the James Webb will have. Another paper that was actually made in this in Bologna was by Cimatti et al. 2008. GMAS, you people know it better, but it's all based on spectroscopic redshift. Again, the blue models are my model 2005. The red are the BCO3 model, and you see that they are very far from the data. And the green is a new release, private indication of Bruzo-Allen-Charlot called CB07, where, as you notice, they have included something enhancing the near-infrared flux. So people were generally happy, but not so much, because what I pointed out there, it's harder to include the TP-AGB, but the other models here just show BCO3, Pegasus, and Starburst 99. I concluded in this paper that their contribution of TP-AGB is either not included or negligible. It was not clear from their paper whether they, to what extent they did, but you see that there is a sizable difference. Now, then the things evolved, and there was a strong revision or discrepancy, call for discrepancy for the calibration of my model. So, as I mentioned before, and this is crucial, and this is tantalizing to notice that the galaxy evolution depends on the ages of Milky Way and globular and Magellanic Cloud star clusters. This is back to my calibration of 98. You see, this is the age, and this is the fractional contribution of the TP-AGB. And this is what Renzini and Francesco called the AGB phase transition, which is that this phase becomes very important around 1 billion years due to a good combination of stellar mass, lifetime, and the envelope, because we should not forget that this is an envelope burning phase and not a core burning phase. And therefore, low mass stars won't have much envelope, and they don't do much in the AGB. And the high mass stars evolve far too quickly, and again, they don't do much of the TP-AGB. So this was kind of known since the 90s. So instead, there is this golden spot in the middle that, with the ages that I used for my thesis, peaked at 1 billion years. Conroy and Gunn revised the same calibration because they have essentially made a remade of my models, and they did two things. First, they used different ages, on which I will comment immediately, for the calibrating globular cluster. And also they used new data for the cluster that they call superclusters, that also Gustavo Busual contributed to obtain, in which the individual clusters are actually grouped in bins. This was already done by Frogel, by these guys that I used, that is Frogel et al. 90. But the bins were taken larger. And the effect is that if you notice, there is hardly a jump to the red, which is instead shown by my model, and instead a smooth evolution, which also is contributed by the red giant branch. So we'll come back to that. So essentially, what Roy has concluded is that MO5 strongly overestimate the AGB, but also get the peak age incorrect. Their proposed peak age is 3 billion years, when the stars is actually pretty small, and also with much less flux. So you see there are two things, the onset age, but also the energetic of the phase. And from there comes a number of work that try either to confirm or to confute all this stuff. And they segregate it to high redshift and low redshift. I will come back to that. So there were work saying, well, actually, but we keep requiring high flux and high TP-AGB. This work that I will show you soon will say instead, no, the AGB is much weaker, BCO3 is much more correct. And also at low redshift, some of this work have been completely unattended in the literature, especially this work who already detected feature. This work came out in 2023. It is actually saying the same thing as these guys. And again, the literature complete. And then there were these two, essentially. I will show you that this actually could have not detect the feature as clearly explained in this paper. So let's say there is a strong debate. And the thing is, photometry was fit for galaxies using different strategies. So the main work that called for a stronger revision of MO5 is this work that is based on BCO3-based photometry redshift, and also strong assumption on what type of galaxies you put in this diagram, which is called the post-starburst. So you essentially impose a sort of a star formation history to the galaxy instead of deriving it from the spectra. And then you decide that the post-starburst will have a fraction of this AGB, which can be 0, but apart from that. And that gives you this plot in which the BCO3 fit much better the data, and MO5 not at all, overestimate. This plot was based on spectroscopy redshift, concluded exactly the opposite. So it was kind of a conundrum in the literature. But we are diligent scientists, and we've been called, and we did our revision. And here the work of Laura Greggio was really important in setting the new calibration. So I show you what I will tell you here is, again, the calibration is an optical to near infrared color as a function of age. Here there are the clusters that have been binned, and for which we use new tracks from Padova with better detail of that ages and the mild overshooting, mild if not 0. And so the red point defines our new calibration. So the AGB phase transition is still there. It onset, however, at an age of 0.6 degrees. So a bit later than what I used based on the ages of the 90s. I mean, science progresses and things go on, so I don't mind. But it is important to notice that this onset is dependent on the ages of the cluster and the tracks with which you use it. The other thing is the effect on the total. We also weighted clusters, but differently from the supercluster used by Roy and Brusual that are these blue diamonds. And so we actually find, though with the generous error bar, this type of behavior. So based on this calibration in age and energetic, I calculated these models that, because they appear in this paper 2013, they are called M13 without any other particular meaning. They are essentially MO5 with a change in the TP-AGB crucial thing. If you have any question, tell me, because this will be very important what I say. A comment on the age. We have, and Laura took care of this, different type of ages. We stick to ages determined from Turnoff. What Roy and Brusual did instead is to use this paper, Kerber et al., and there are others, that instead get an age as the best compromise between the main sequence and red clump, which is we learned at school, quite incorrect, because the turn-off is a strong age indicator. The red clump depends on many other things in the stellar tracks. If you take a compromise on an evolved phases, you get actually, if the red clump on set later, the compromise age becomes larger. And this is how we explain 2013 why they pushed the onset of the TP-AGB to 3 billion years, which seems very high. So we think one of the problem, we still think is a problem, the data will confirm that, is how the ages of the globular cluster have been assigned. We stick to turn-off ages. In 2016, we decided to actually compare with Daddy, with Emanuele, all these three models, M05, M13, BCO3, to 58 high-redshift passive sort of galaxies with spectroscopic redshift. The M13 were doing well, but in fairness, without including reddening, M05 was still giving the minimum chi-square to all this data. When reddening was included, something that was known, reddening is a parameter in the CD fit, degeneracy take the place, and you get actually a lot of excellent fit with BCO3. But they might imply different type of reddening. So sort of the field remains sort of there from our perspective. The general community married completely the verdict of Conroy and went back to BCO3 all along, and they withdrawn the CB07. But the thing is, what would be the conclusive evidence would be the direct detection of TP-AGB spectral features. Because photometry is, of course, affected a different type of degeneracy. But if you see the carbon-2, there's nothing that you can discuss. In fact, that luckily happened. And so this is the paper. You probably have seen it. It's under review. We got 3 positive referee reports. That's why we feel like putting it forward. The first referee said that this is an exceptional result. It makes us very happy. It could have been different, but he said it's this. So this is the galaxy spectrum with spectroscopic redshift at 1.82, near infrared. And this is amazing because, you know, guys, when I saw this spectrum, I was thinking about my models with all these bumps. And you see the bumps in the galaxy. And that's amazing because it's the first time at those high redshift that you see all these things. She, who lead that, has done an incredibly careful identification of all these species that are actually, we will show, unique to TP-AGB stars. The difference between the two lines is the arrow. This is an incredibly high signal-to-noise spectrum, which also challenged the models, because when you have such a high signal-to-noise spectrum, you have to recover all the wiggles. It's actually worse than what we're using the optical, for which there has been a lot of empirical library things to make it. So I should also say that this galaxy was in the archive of the Sears collaboration. And for some reason, Emanuele was the only one picking it, which is also very interesting, right? They tell you, yeah, you can ask for more data. First, look at the data you get. So this is all the merit of Emanuele, because he was never convinced by these things, because he was fitting galaxies since a decade, and then he found this spectrum here. So the first things we did was to compare to stars, also because the Nature paper wants simple messages. And in these two plots, you see the observed galaxy spectrum is the black, the carbon-rich star, one representative is the green, and you spot that. That's also allowed us to identify all these edges. To the right, you have the oxygen-rich stars that are responsible for other type of bumps. Note that, and I will come that later, it is also not trivial for the TP-AGB what mixture of carbon and oxygen-rich stars you have. So there you need to make assumption on the metallicity dependence on these things and the effect of the dredge up. I use a particular recipe that I will like to tell you later. It seems to work indeed. So, okay, and that's the comparison to the models. Offset, but then I will show you the fit. On this side, you see the comparison to MO5 is the green, and then 13. The nodes are the features that are identified. And on this side, you see BCO3 Echo Roy 09, the latest version of models. And you see, in fact, that they can identify far fewer features. They also release different ages, and we'll come to that later. Interestingly, a couple of weeks ago, there was this paper on a new huge James Webb Space Telescope project in which, around the group of Mariska Creek, in which they say that, in fact, it's hard to recover most the features, up to 7,000, so not even in the, so you see here you have the rest frame wavelength, here the observed wavelength, so 7,000 is about here. There are already CN features, but it's quite a narrow spectral range. Already it's difficult with that, and that's also, and they conclude, pointing to our paper, that probably there is some evolved star missing. They don't call it with a name for some reason, but they say that is that. So when you do the fit, the full, you get this horrendous high chi-square because of the very high signal to noise of the spectrum, but with a very clear trend. What the literature called is not me calling it, but they have baptized BCO3 TP-AGB poor, then TP-AGB light, then TP-AGB mild, and then TP-AGB heavy. Yeah, life is like this. So MO5 gets this worst chi-square, but it's mostly due to requiring a different star formation history, including young population. So here, in reality, we think is the effect of the onset age, which is more homogeneous in this type of models, rather than the feature, because most features are actually well represented by MO5. Interestingly, the results do not depend on the fitted wavelength range. We have broken the spectra, but in reality, we get the same result. We have also considered further models. I didn't want, to be honest, to plot in a Nature paper unpublished model put forward 7 years ago without any description. But we decided to do it because the extragalactic community is making abundant use of those. But you see that they are here, BC16, and they actually, they are basically identical to BCO3 in this over 1,000, but here they lack somewhat flux. But we cannot comment any longer. But we also included the Vazdeckis E-Miles models. And the reason why we included that is because you have seen initially from my thesis plot, when the TP-AGB rise, there is also the rise of the red giant branch. Some of those features may be due to giants. To what extent we fit, and in fact, they couldn't provide a good fit. If the galaxy spectrum would have been mostly due to red giant branch of an old galaxy, this model could have provided the best fit, and instead is well below actually most of the others. We already knew, but you need to convince yourself in a bit more quantitative way. And the other one that we included at SSP just published based on the X-Shooter library. That's very important because in this case, all phases, not only the TP-AGB, are based on empirical atmosphere. So we thought, let's see what the empirical atmosphere go, and the TP-AGB's model a la Colibri that are the latest tracks of Padova. And in fact, we get 67 chi-square, if you remember, it was worse than others, and also old age and low metallicity, and most features are not recovered. So that's interesting, and that to me says something probably I said already. These tracks calibrating on the extended star formation history do not get the actual TP-AGB. It's probably the calibration or it's something else. They also, however, in this paper, they either don't have the right carbon stars or their fuel consumption is far too small. So now comes a paper that was made here we did together with France that shows a little bit why, in reality, you have to pay attention to all phases, but also it's not easy to trade one phase for the other. The 1 gigayear epoch is quite critical because it also sees the onset of the red giant branch. In this plot, you see the bolometric calibration, the red giant branch versus helium clump stars in Bologna in light, and there was in number. I don't know if I put it as a function of ages of the first generation, but still with a good error bar. And you see that these are the tracks that I used in my model, and these are the data. And these were the Padua tracks with strong overshooting. They actually predict a quite later onset of the red giant branch, which means part of the failure of the fit of those models is also that they don't even get this type of red giant branch, well, let's say, at an epoch that actually most accommodate the data. So there are two things to include, and the golden combination seems to be good. One word on the chemical composition, and apologies for this didactic slide that I took from some lectures. In reality, we are calibrating fuel and lifetimes on Magellanic cloud clusters that are roughly half solar metallicity, while we know that massive galaxies are actually metal rich. Now, Renzini and Voli actually provide a recipe, a theoretical recipe, for scaling the flux in general as a function of metallicity for individual stars. So in my paper 2005, I extended their calibration to the modeling of population. And the thing is, the more metal-rich a galaxy is, the more oxygen rich feature will have. Instead, the more metal poor, the more will be rich by carbon stars, something that is very interesting because it can affect this very high-redshift James Webb data that already see carbon features. So in general, in my model, there is less fuel in carbon stars, the more the galaxy is metal rich. Now, we have not done this quantitatively because this is part of the work that we're doing now. We seem, in fact, to see that the galaxy is metal rich and is very happy with my model at time metallicity, which contain more oxygen-rich stars over carbon stars. That's the scaling that I propose. I'm going to the end, but you feel stop me when you like, because I already started late. But I needed to also give granted to Miriam and Pastoriza, because effectively, AGB features were already detected in local galaxy spectra by this group in Brazil using MO5 and showing that other models would not match. These are local star-forming galaxies. We use, or we found a high-redshift galaxy that is quiescent, and that's a boost the TP-AGB simply because there is no dilution from other stellar generation. So that's very convenient. But these guys, actually, in near-infrared spectrum, local galaxy, where you don't have the redshift and all this stuff, ambiguity, they already found that. And show that, for example, if you fit, this is a spiral galaxy. If you would fit with a model like MO5 with TP-AGB, you obtain, look just at this plot, this is a bit optimized population synthesis, a distribution of ages in the spiral, which is quite smooth and suggestive of an exponentially declining model. So all ages are populated. If I remove the TP-AGB, suddenly your spiral galaxy has no population of 10 to the 8 or 10 to the 9 giga, which at least to me seems a bit contrast. It has a very old population and something very young, like if the fit avoid exactly that. The same happen, in fact, if you try to fit with BCO3. This is all in the paper Riffel et al. 2015. Again, you have a hole at the typical ages of the TP-AGB, which is suggestive that, in fact, there is something in the model missing that happened exactly at those ages. So, give you the summary, and then I give you some outlook that we are doing now. I think the James Webb has finally detected TP-AGB feature. This is seen by simple comparison with stars, but also through the evolutionary synthesis for various recipes for the thermally passing asymptotic-giant-branch phase. The MS13 that works best seems to suggest an onset time of 0.6 giga and an evolutionary mass a bit smaller than 3 solar masses. This has effect on chemical evolution, because it's not only the modeling of galaxies. There are models that are they're actually quite strongly disfavored, and they take the TP-AGB from these calculations. which include certain mass loss or others. So we will see. The effect on galaxy evolution is to have lighter and younger galaxies, something we said back in 2006. The Nature paper contained 3 galaxies, so we didn't push at all, but I will show you more galaxy now. Something we are doing is to refine the modeling for specific TP-AGB features in order to determine abundance ratio of critical elements. The near-infrared could actually give us this chance. Now, very quickly, I have 2 slides. Tatiana, you have to tell me when to stop. Let's recall why the TP-AGB matters on galaxy evolution. I just borrowed this paper, but there are many others in the literature. So let's just look at this plot here. This is the stellar mass with BCO3 over the stellar mass with MO5. Because the galaxy model becomes redder at a younger age, you get a lower mass to light ratio, and hence a lower mass, but also younger galaxy. And we wonder how much this affects the crisis of lambda CDM that the James Webb Space Telescope data has actually highlighted. Because at redshift 10, you're not expected to have a 1 billion year galaxy, but these are the ages that they obtain, and that's why their masses are so high. So the thing now, it will be open an interesting revision of fitted data. In progress, we have now 10 more IZ galaxies that Lou is comparing, and we are actually finding exactly, confirming fully the result of the Nature paper. And here I just made a plot. The stronger effect is on the age. On all these plots, you have the chi-square, M13 on the y-axis versus BCO3. That's important to put versus BCO3 because this essentially most work in the literature are based on these models. So the chi-square is generally better, in all cases. The age is substantially younger. The stellar mass is younger, again, due to a combination obtained with the same fitting code, etc. And the metallicity is also a bit smaller. This is a smallest effect. The BCO3 tend to give you very high metallicity, obviously, because they need to pump up on the feature of the near-infrared without the TP-AGB. And I think I finished, and I leave you with that instead of the summary, if you agree. Thank you very much.
Are there questions? Please.
Thank you very much for your presentation. So, for what I understand,